say that you want to do unsupervised learning. So what we mean by that is that you know the x's, you do not know the y's, you do not know the labels, and you want to come up with sensible theta and pi for those x's, even though you do not know the y's. Okay? So to remind you, so pi j is the probability that y is equal to j, and then you can define theta ij as the probability that xi is equal to 1 given that y is equal to j. So the first thing that we'll do is we'll just guess at theta and pi, and based on that, so we'll just assume that the guess is correct, we'll try to give some kind of estimate for the y. How can we do it? Well, we can't get y directly, but what we can do is we can compute the expectation, given that we guessed theta and pi correctly, of this kind of variable. So this is going to be the indicator variable that says yi is equal to 1 given the xi that we have. Okay, so what is this? So we don't know y, right? So we're left with just saying, well, if we knew y, this would either be 1 or 0, depending on whether yi is 1 or 0. But we don't, right? So all we know is we know the theta and the pi and the x, and we're trying to compute this kind of expectation. So if you assume that y is either 0 or 1, it's very easy to see that the expectation of this kind of indicator variable is just the probability that yi is equal to 1 given xi. Okay. So this is just mathematically true. Now, once you know this, well, this thing you can actually compute, right? How do you compute that? Well, you would just say, so the probability under theta and pi that yi is equal to 1 given xi, so just use Bayes' rule, right? So say that this is going to be the probability of xi given yi equals 1 times the probability of yi being equal to 1 divided by the probability of xi. Now, if you know theta and pi, you know this. This is just pi 1. If you know theta and pi, you can use this by factorizing this expression and using the various theta ij's and 1 minus theta ij's in order to compute this guy. Okay? If you know this guy, then you know this guy. Why is this useful? Well, this is useful because now that we have some kind of estimates, and this is going to be a number between 0 and 1, some kind of estimates for the y's, we can now try and estimate the theta and pi again. How would you estimate theta? Well, in order to estimate something like p of x2 equals 1 given y equals 0, something like that, what do you need? You need the number of examples such that x2 is equal to 1 and also y is equal to 0. And then you also need the number of examples where y is equal to 0, then you'll divide them and you'll get your estimate. That's your naive Bayes estimation, right? Now, how can we get that? Well, we can use this guy, right? So we can say, okay, we don't know exactly how many times x2 is equal to 1 together with y equals 0, but what we can do is we can say, well, let's just do it like that. So let's compute the expectation. So this would be the number of times that x2 is equal to 1 and y is equal to 0, except we don't know that, so it's going to be kind of like an estimate for that. And that's going to be the expectation under theta and pi of the sum for all the i's such that x2 is equal to 1 of this kind of thing, of I, yi equals 1 given xi. Okay, and that's just going to be the sum of those guys. We know how to compute this. So how to interpret this? Well, one easy way to interpret it is to just say, okay, so we computed those estimates for the y's. There are numbers between 0 and 1, and then we just pretend that this counts, for example, assuming that's 0.8, as 0.8 examples of y being equal to 1 and dog appearing in the email. It's also going to count for 0.2 examples of y being equal to 0 and dog not appearing in the email. Okay? So we can use this. Similarly, we can compute the number of times that y is equal to 0 in total. And there you are. You have the counts. Once you have the counts, you can estimate both the theta and the pi.